Se më lejoni, po fillojmë gradualisht. Njëherë përbëj një prezantim të shkurtër të Gramozit në gjuhën shqipe dhe pastaj fillojmë në gjuhën angleze. Do thënë, mirë se vini në seminarin e radhës të Departamentit të Matematikës në Universitetin e Prishtinës. Kam kënaqësi që ta prezantoj para jush folësin e radhës, është Dr. Gramoz Goranci, i cili aktualisht është në ETH, po ka qenë student i yni në Universitetin e Prishtinës, edhe faleminderit shumë Gramoz që ke gjetë kohë edhe vullnet për me bëjt një prezantim para nesh. Shpresoj që do të shihemi përsëri në Prishtinë ku jemi pa javën e kaluar. So I have the distinct pleasure of introducing the next speaker in our series, the Math Department Seminar at the University of Prishtina, and the first speaker for this year 2023, Dr. Gramoz Goranci from the ETH, Zurich. He will be speaking about Vertex sparsification in dynamic algorithms and beyond. So his talk will be about 50 minutes long, and then we can ask questions and make comments if we have them. Thank you so much. And now I will make you a co-host, Gramoz.
Okay, great. Thanks a lot, Sindren, for the nice introduction. Faleminderit shumë. Dhe është nderë dhe privilegj me qenë këtu. Edhe me një tregu diçka për çka punoj ose çka bëj. Let's switch to English now. And let them take you slide. Apo e shihni këta, po është në full screen mo. A është në rregull tash? Po është në full screen mo? Në rregull. Okay. Okay, so today I'm going to talk about vertex sparsification in dynamic graph algorithms, and I'll try to tell you also a bit more beyond dynamic graph algorithms. And this is going to be a survey talk on things that I've been working on, and I'll also get a bit into technical details. Probably I won't be able to cover everything throughout the whole. I mean, I have probably around 30 slides, and I want to go a bit slow, and considering that there are different backgrounds here, I would like to go a bit slower, but just feel free to interrupt me whenever you have any question, and I'm very happy to answer those. And that's also the purpose of like why I'm giving this talk, because I want you to understand something out of it, or get something out of it. Okay, so let's start with reviewing this notion of graphs, this basic notion of graphs. So I'm pretty sure everybody is familiar with this, but let's just have a quick recap. I'm given a graph G, and I have a set of nodes which I denote by V, and I have n nodes, so the cardinality of the set V is n, and I have also a set of edges, and these edges connect any two nodes. For now, let's assume that I don't care about direction, so this is an undirected graph. So when U is connected to V, then V is also connected to U. And graphs are objects that have been studied a lot in many disciplines, including math, computer science, biology, economics, social sciences, physics. And they usually are used to model binary relationship between different entities. And you could think of, for example, road networks, where a vertex would correspond to a city, and an edge connects to cities if there is a road connecting to cities, right? Or you can think of social networks, for example, the Facebook graph. So each node in the Facebook graph is a person, and if two people are friends or two persons are friends, you essentially have an edge connecting these two. Or collaboration networks, for example, if two people write a paper together, there is an edge connecting. Okay. And let me try to motivate one of the basic problems in graph algorithms. So this is basically, this area is an intersection of graph theory and mathematics, as well as algorithm design or computational complexity. So let's say that I'm looking at these two neighboring cities in the border crossing Germany and Austria. So I would like to find what is the shortest path from Munich to Vienna, okay? And as you see, this is a snapshot of Google Maps, and there is behind an algorithm that does this for you. But the question is how is really this performed? You know, what is the backbone structure underlying this Google Maps. It turns out that what you saw in the previous slide can be essentially written down as a graph problem. So let's try to simplify things a bit and say that I'm looking only at big cities. For example, I'm just looking at some cities like Linz and Graz and Ingolstadt in Germany. And each of the cities correspond to one of these black vertices. And U corresponds to, say, Munich, and V corresponds to Vienna. Here, these two vertices. And to the connections, as I said before, you have a connection, you have an edge connecting these two cities whenever there is a road that leads from the city to the other. And let's assume for simplicity now that there are no weights, right? So the distance going from one city to another is 1, which is a pretty strong assumption, but let's do it for the sake of simplicity. And finally, you want to find what is the shortest path now, distance between this vertex U and this vertex V, okay? And see here, over here, you see it's 4. But, you know, if there are weights, then it could potentially be more, and things like this, right? So this is the classical assumption algorithm design. So usually you're given a graph, you're given this set of distinguished vertices U and V, and you would like to output the shortest path between U and V, okay? And this problem is fairly well understood. And for those who have done algorithm design, and I think this is covered, I've done it myself when I was a student at University of Prishtina. So we saw the Dijkstra's algorithm that solves this problem in time linear in the number of nodes and edges, ignoring some small terms like polylog terms in the running time. Okay, fairly well understood as a problem. But now the reality is very different. So what we see in reality is that these graphs that we are looking at are highly dynamic. And what do I mean by that? For example, if you look at a Facebook graph, and the Facebook graph is pretty big because Facebook has at least billions, the size of the Facebook graph is roughly billions of nodes and edges, right? And some statistics show that, for example, the number of new users added to the network is roughly 400 per second. Okay, so this is being changed and being updated incrementally a lot. Or if you look at this Google Map example that I gave you in the last slide, what you see is that, for example, these edges that connect roads change capacities or change lengths over time. What does this mean? For example, during rush hours, the capacities, so the length increases, right? Because it takes you more time to go from one city to another. And for example, during night, overnight, these capacities are smaller because the roads are sparse, right? There aren't many cars going through this road that connects cities. Okay, so as you see, in reality, this assumption in classic algorithm design that you're given a graph as an input doesn't really make sense, because in most of the applications that we care about these things, so in applied things, not from a theoretical point of view, but from a practical point of view, these graphs are highly dynamic. Okay? And so the challenge is what I described, and the whole goal of this talk is to tell you about this, how do we design dynamic algorithms. And these algorithms, you can think of this as the science of trying to avoid recomputation from scratch. And why am I saying this? Because whenever you have a change in the network, what you could do is something very trivial. So you take the change, you update it, and then you run an algorithm from scratch, right? So you take an algorithm, for example, Dijkstra's algorithm, and then you run it from scratch. But this is trivial, and you would like to do something better than this, okay? Because that's expensive. If the Facebook graph is billions of nodes and edges, you cannot afford after a user is being added to the network just running the whole computation from scratch. That's just unfeasible. Okay, so let me try to tell you a bit more formally what I mean by this. So let's assume I have this graph on the left-hand side over here, and edges are being inserted and deleted. So I have these two types of updates. I have edge insertions and edge deletions. So now let's assume that this edge over here is being deleted. And now you can think of the dynamic algorithm as follows. It must be able to process this update. So it takes this update from the graph G, and then it does some work in the background. Okay, so you think of this as like a black box. And let's just say you have another update, which happens to be an insertion connecting these 2 points over here. Again, you you take this update and then you tell the dynamic algorithm to do something about it, and it's going to do something about it. And at any point of time, a user can ask a query. And it can say, okay, I give you any two arbitrary vertices now in this underlying graph, in this current graph. So the graph which has processed the changes, what is the shortest path between you and me in the current? So if you try to just report the old shortest path of the graph that we started with, this is definitely going to be a bad approximation. So there are examples where this is horrible. So you will need to do something. This dynamic algorithm needs to do something to be able to answer these queries somewhat exactly or approximately, depending what kind of relaxation we allow. And so finally, this algorithm needs to give you an answer, right? And the answer it gives you can be an estimate, and this estimate could either be a distance estimate, which exactly preserves shortest path distances, or it could be an approximate, okay, depending on what you want. And there are two quantities that you care about here. One is called the update time. So what is the time that you need to process these updates? So these are insertions and deletions from the underlying network. And the second thing that you really need to care about is query time. So what is the time you need to handle these queries, okay? And as I said, there are trivial algorithms. So for example, you can also just ignore updates. And then whenever you have a query, you process all the updates and then you run just a static algorithm from scratch. But that's not what we want. So these are trivial algorithms, and we want to avoid computations from scratch because these are expensive if the graph is huge. So we want to do something low, sublinear in the size of it. Okay, so this is the definition of dynamic graph algorithms, a bit more formally. If you have any questions, let me know. If not, then I will continue. Are there any questions? Do you understand the model?
I think it's okay so far.
Okay, cool. So I'll continue then. So why do we care about this? You may ask, right? I mean, I tried to tell you why you care about this, but why foundations of this? So why should we study this from a theoretical point of view, right? Okay, so number one motivation, there are tons of algorithms that do such kind of work, so do dynamic graph algorithms in an explicit or implicit way in many areas of computer science. So if you look at data mining and network summarization, tracking communities, social networks, algorithm engineering, where you try to actually compute this good shortest path in road networks or Google Map navigation systems, or distributed and parallel algorithms. So there is tons of literature being done in applied communities of computer science. And unfortunately, most of them, or I would say a very large fraction of them, just do heuristics. So they don't really understand what's going on. They try to find some algorithms that work good on some instances, but then in some other instances, they perform very bad, or they have some assumption about how the data behaves, or they come from a specific probability distribution. So usually, so these studies are useful and they are being used in practice too, but it's very hard to understand whether you know these algorithms that are being used actually give you the answer for all the instances that could be out there. So this is what we want. So this is like a worst case analysis of everything we'll try to do here. So first, we just try to understand what are the extensions and limitations of this technique. Okay, so this is the first trivial thing that we'd like to do. As a theoretician, you try to understand what the applied people are doing and try to prove some theory about it, right? So the second motivation is a bit more theoretical, and actually this is how I got involved into doing this. It turns out that in addition to this relation to practice, there are a lot of algorithms that are covering combinatorial optimization, like the maximum flow problem, and I'm going to talk about this. So this is one of the basic problems in combinatorial optimization. Then you have matching, street packings, multi-commodity flows, graph sparsification, and all of these algorithms actually use dynamic algorithms as a black box. Okay, so what do I mean by this? So usually, if you want to solve, for example, max flow, you will use dynamic shortest path as a black box. So it turns out, so if you use iterations of shortest paths in a very specific way, you can speed up static algorithms. And there is a big area in algorithm design nowadays where you try to achieve very efficient running time for solving a problem. So I'm not only interested in solving, for example, max flow problem in polynomial time, but I want to solve it as soon as possible. Say near linear in the number of nodes and edges. And these questions are really challenging. And that's where dynamic algorithms are kicking in and actually being very helpful in speeding up this static, very famous static algorithms. Okay? And I'll talk a bit about this depending on how much time I have today. So what is the ultimate goal? To summarize, this is the ultimate goal is to understand the dynamic complexity of many graph-based optimization problems. And I'll talk a bit about those. Okay, so now let's go a bit to the. So when I presented the name of the talk, and when Chandran presented it too, he said like, what is the use of vertex sparsification, right, in dynamic graphs? So today I will try to actually give you a tool which is very useful to construct dynamic graph algorithms. Okay. And I claim this tool is very generic. Maybe you will see one application of this, but it has been applied in many other problems. And to do that, I will first need to tell you about graph sparsification. Okay, so this notion of graph sparsification is very natural, one that you would expect, but let me go through it. So what is the general idea? The general idea is I have a big graph and I want to approximate with a small one. So this is very vague. So what is big and what is small? Let me try to redefine this bit. Let's say that I'm actually interested in bringing the number of edges down. Okay, so I have a very dense graph. Say the number of edges in the graph is n squared and the number of nodes is n. So this ratio is proportional to n. So it's a very dense graph. And a dense graph, for example, if you look at the complete graph, this is a very dense graph, right? And you would like to approximate with a sparse graph. So the node set remains the same. So the nodes remain intact, but I would like to have fewer edges. And you might ask, okay, I can just go and delete edges. Why is this a good problem? Well, you can do that, but then you want to preserve something too, right? This is the whole idea of sparsification. So you want to preserve this very dense graph with a sparse one, and at the same time, you want to preserve some property, graph property that you care about. If you talk about shortest path distances, and these are called spanners, you would like to construct a sparse graph that preserves shortest path distances. So for example, as you see, this edge connecting these two vertices on the right-hand side doesn't exist here anymore, but I have a detour, right? I can actually construct another path between these two edges, which is not the shortest path, but I hope it's not far away from the shortest path. So it's a good approximation for shortest path. And the same I can do for, okay, so now I haven't defined cuts, but it's the same you can do for cut sparsifiers, which are closely related to flows, and spectral sparsification, which I'm going to talk today about. And so on and so forth. So this is the whole idea. Just to summarize again, so you're given a graph and it's dense, so you want to sparsify it. You want the number of edges in this graph to be proportional to the number of nodes, say m polylog. And at the same time, you want to preserve some property that you care about. And there are so many properties that you care about, including shortest path distances, cut structure of graphs, and graph spectrum. Okay. And so this has been used in dynamic algorithms before. So we are not the only ones to actually, try to leverage sparsification in terms of dynamic algorithms. But I will show you where is the novelty. But the caveat here is that all of these applications do suffer from this linear barrier. So why is this the case? Because I'm just reducing the number of edges, okay? So this is sublinear if the graph is dense, but if the graph is sparse to start with, for example, Facebook graph is sparse, social networks are pretty sparse, okay? So you're not getting any gain in the running time at all. So because what are all of these dynamic algorithms do is that they maintain some dynamic sparsifier of this graph, and then they just run from scratch on the sparse graph instead of the dense graph, okay? And so this is not very useful, I would say, if you want very fast algorithms, but can give you something non-trivial that goes beyond that sublinear thing that I mentioned at the beginning. Okay, so now I'm going to start talking about the main notion of this talk, I would say. This is called vertex sparsifier. So unfortunately, I would say that vertex sparsification is not as famous as graph sparsification or edge sparsification that you saw from the previous slide. And somewhat it has been overlooked, and it has gained probably momentum in the last 10 years or so. And yeah, I would like to see more work on this, and there's been some exciting work. And so before doing the selling point, let me try to tell you what this problem is about. It's actually very fundamental too. So you're given a graph G, and now the set of vertices is partitioned into two parts. So this red and black vertices, okay? And then these red vertices are vertices that you care about. These are widely referred to as terminals, okay? So these red vertices are vertices that you care about. And the goal is to construct a smaller graph H, which you call a vertex sparsifier. So now this smaller graph must preserve some graph properties, so I say shortest path between the red vertices only, but it doesn't care about black vertices at all, okay? So you want to be able, in a sense, to reduce the number of nodes, so get rid of as many black vertices as possible, so that the shortest path between the red vertices is preserved. Okay? So this is the idea, and it doesn't have to be shortest path. It could be anything. It could be max low effective resistance. I mean, but shortest path is the easiest to relate, I guess, because everybody knows what shortest path is. Okay. So another thing is that this is a bit more formal, but you can ignore this if you feel like there is a lot of math going on. But what is the goal here? I want this sparsifier to be small, right? I want this H to be as small as possible. And I want the quality of approximation to be as small as possible, right? I want this alpha to be close to 1. 1 is ideal. Usually 1 is not possible. Maybe 1 plus epsilon or some constant factor approximation would be possible, okay? And this notion here is just referring to some sort of approximation. Think of it as multiplicative approximation of this graph property that we care about. Okay, so this is the idea of vertex sparsification. Now we want to get rid of vertices. It's not enough to get rid of edges. Okay. So how were previously vertex sparsifier used in the context of dynamic algorithms? So usually, if you assume something about the underlying graph, so in graph theory, there's certain classes of graphs. So you can have general graphs; these are the most generic one. You can have planar graphs that you can draw in the plane without any intersections, except at the endpoints, and you can have many other graph structures. And so if you have such assumptions of the graph topology, then vertex sparsifiers were used before. So now in this talk, I will try to tell you something about general graphs. I will not assume anything about the topology of the graph. And I will also mention what other properties can be maintained dynamically beyond those that are presented here. And more importantly, what's important to me in general is not about just solving one problem, but also building theories. And an obvious question or a natural question is whether there is a meta theorem relating vertex sparsifier to the design of data structures. So what do I mean by this? Can you somewhat write down the condition of saying, oh, if I have a vertex sparsifier with these qualities, then I have a dynamic data structure for solving a dynamic graph problem. Okay? So that's what I mean by a meta theorem. So what are the properties that I need to maintain a graph property dynamic? Okay, so this is more or less the intro, and then let's get a bit more technical. So now I'll switch gears a bit and try to be maybe like more math oriented, or at least consider a problem which is not as simple to capture as the shortest path, like find the distance between 2 points in a graph, but somewhat related if you view it in an algebraic sense. So before doing that, let me try to tell you what a Laplacian of a matrix is. I'm sure those that you have done mathematics have seen this before. So this is called the discrete Laplacian. So whatever I'm talking here about, I'm talking about discrete structure. This is a combinatorial optimization. I'm not talking about continuous objects. Okay, so let's assume I'm given a graph G, and there is a very, I would say, natural interpretation if you view this graph G as a resistor network. And what do I mean by that? Every edge in this graph G corresponds to a resistor, right? And if I take any graph and I view each edge as a resistor with some specific resistance, for sake of simplicity here, every resistance is 1, then I have a resistor network, okay? So every graph gives me a resistor network. And let's assume, in addition, that I fix some n-dimensional vector sitting on the vertices of this graph, which are widely referred to as voltages of the graph, okay? And the Laplacian, one way of defining this, okay? So there are many equivalent way of defining Laplacians, but one way of defining this, which I really like, is this notion of Laplacian being the unique symmetric n-by-n matrix that realizes the following quadratic, okay? And so this is the definition of what a Laplacian matrix is. Some of you might have seen, this can also be defined as taking the degree matrix minus the JCC matrix of the underlying graph. So that's equivalent. And so now, for example, you want to, so the whole point that I want to make, at least in this slide, is why are these Laplacian systems useful? And now let's say I want to solve so I have a matrix and I want to solve a system with respect to this matrix. And why are these useful? Because if you want to compute voltages when you induce one unit of flow from S to T, so you're putting a 1 here and a -1 here, a 1 at S and a -1 at T. So you're putting 1 unit of current to throw through this network, and you ask what is the voltage difference induced on the edges. And to compute the voltage differences, the amount of current that actually runs through this network, you will need to compute these voltages, right? And these voltages can be computed just by solving the Laplacian system. So what is a Laplacian system here? So I have this n-by-n Laplacian matrix. So I omitted G there, but doesn't really matter. And then I have this voltage vector and dimensional vector X. And this is called the demand vector. Okay, so it's one at S, it's -1 at T, and everywhere else is 0. Okay. And this tells you so that you can compute these voltages on the network just by solving this system. And now, since I do algorithm design, I care about running times, right? And the question is, how fast can I solve this system? Okay. So a trivial question to this answer is you can do it in n cubic time. So this is just a high school Gauss elimination. And so n is remember, n is the number of nodes in the loop, okay? So you can solve it in cubic time. And then there is this beautiful work that started by Strassen in '69. So basically he says that you can actually get better than n to the cube trivial running time for multiplying matrices. And if you multiply matrices efficiently, you can also solve systems efficiently. There is like a very easy reduction. And this automatically gives you an improved algorithm. Actually, the best running time nowadays is 2.37. It's conjectured to be n squared, but nobody knows how to do it. And yeah, it's one of the most famous problems, I would say, in complexity theory. To get a fast matrix multiplication which runs in n squared. But there is a caveat here. This matrix L has some structure. In particular, this matrix L is related to some graph structure. So there is more symmetries that we can exploit rather than just saying this is any arbitrary matrix. In fact, this is a PSD matrix, but is even more structured than a PSD matrix. Okay. And for this specific matrix, there's this work who also won the Goethe Prize by Steeman and Tang, which shows that you can approximately solve the Laplacian system in near linear time. So essentially, this is type up to polylog factors because m is the number of edges in the underlying graph. So this is the number of non-zero entries in the Laplacian. So it takes you m time to just write down the matrix, right? And this theorem says that you can actually solve Laplacian systems up to very high accuracy in nonlinear time. And I will not get much into the details of accuracy here, but I'm happy to talk about these if anyone is interested. Okay, so hopefully this is clear. So these are the Laplacians. Why do we care about them? And now we even know that we can actually solve systems with respect to these Laplacians, linear systems in near linear time. And by near linear, I mean near linear in the number of non-zero entries in the Laplacian. Okay, so let's look at a very specific measure now, which is related to shortest paths, if that helps you with the intuition. So if I said again, so remember I said 1 unit of current from S to T, from this vertex S on the left-hand side to this vertex T, and I asked what is the voltage difference induced now. Okay, and this notion turns out this quantity that you get, what is the ST voltage difference when routing 1 unit of current from S to T? This is so-called the effective resistance of a graph between S and T, these two endpoints. Okay, and one way to view this, again, there are so many other, you can also view this as what is the amount of energy burned in the underlying network, or minimum energy dissipation, but doesn't matter, that's more like a physical interpretation. One way to view this in terms of algebra is actually taking a Laplacian, and this LDAG here, LDAGger, this actually is the more pseudo-invertible Laplacian. And if you look at constant number of entries in the more pseudo-inverse the Laplacian, you will actually get f. Okay, this is more like an algebraic way of viewing it. So what is so important about this? It is a very nice concept related to random walks on graphs, and I will talk a bit about that. And so a random walk, essentially, for those that you don't know, you start somewhere, you pick a random neighbor, and then you go to that vertex, and then you pick another random neighbor, and then you're just like walking randomly in the graph, right? So you always move proportional to the number of neighbors. Okay, that's essentially what a random walk in the graph is. And moreover, it defines a metric on the vertices of G. But when it defines a metric, it gives you another way of measuring distances among the vertices in G. So clearly, it's not an L1 base distance. For example, if you look at L1 norm, that corresponds to exactly shortest path because you're just summing up overall distances. You're not asking about the shortest path. But this one will define a metric on G. You can prove that all properties of the metric are satisfied. But in fact, it's going to be an L2 squared metric instead of L1. Okay? So you can show that. And as I said, it's also related to random walks. So now what we look at this dynamic version of this problem. Okay. So remember when I talked before, I said dynamic shortest path, you know, I have a graph, I have the cities, and there are edges connecting the cities with potentially different weights, and some weight changes because of congestion in a network, and then you would like to find what is the new shortest path with respect to now this congested edge, right? Because maybe shortest path was using that congested edge, but this is somewhat expensive now. So here, I'm asking the same question, but now I'm not measuring distances with respect to shortest path, I'm measuring distances with respect to effective resistances, because this is a metric on the graph, and I can measure distances using this metric too, okay? And the whole idea is, can I maintain this approximately this effective resistance with very small update in very time? Okay. So the problem is the same. There are changes on the left-hand side. The graph is being updated. At any time, the user can come and ask, what is the effective resistance between U and V? And you should give an answer. Okay. So the same model. Let me try to convince you that this is not a very easy problem. And in fact, some of the simple-minded approaches that are usually used in dynamic graph algorithm completely fail. And here is one. So let's look at this network. I have a graph. It has 3 layers, and it has roughly n over 3 vertices in each layer. And it's a disconnected graph. So as you see, I have two connected components here because there is no edge connecting this connected component on the left with this connected component on the right. And initially, the effective resistance between S and T is just infinity because I cannot reach S and T in this graph, right? So let's assume I add an edge, then the effective resistance becomes some finite number, fine. That's nothing. Then let's assume I add another edge. Now, again, the effective resistance now essentially becomes, and it was n minus 2 over 3, now it's n minus 2 over 6. You can compute it if you just put these two things into series and parallel. These are like rules that you might have seen in high school physics, probably, when you did the resistor networks. And again, if I add another edge, I just have some constant factor change in the effective resistance. It's not horrible. I could say, okay, now why don't I try this obvious algorithm? So for some time, I don't do anything. And my effective, and I can always report this effective resistance, the old one, because this seems to be like a constant factor approximation to the current one, and I'm happy. And then maybe after a while, I will just recompute from scratch, okay? But this example shows that even after only a constant number of updates, the effective resistance can drop by a lot. For example, here, initially, it used to be roughly n, which is proportional to the number of nodes, so n minus 2 over 9. And it just dropped down to 1, as you see over here, okay? So it's a big change. It's an n approximation. N approximations are horrible. You don't want to do that, right? Okay, so just this lazy way of dealing with updates in the underlying network doesn't seem to be helpful in terms of effective resistance. Okay, so let me tell you what has been done in this problem, towards solving this problem. So there are a bunch of implicit algorithms that were there in the literature, and some also subsequent improvements. So what we essentially know that if you want to compute them exactly, that you cannot do it efficiently. So there are lower bounds that say that you cannot do it. But the good point is that if you allow some very small approximation, like 1 minus epsilon, then you can get sublinear running times. Okay, so, and I've been involved in a bunch of works doing this over the years. So for example, for general graphs, unweighted general graphs, you can get m to the 3/4. So m is the number of edges in the current graph. And so this beats the m running time, which is just computed from scratch, okay? And also works for all pair effective resistance. And you can also get different trade-offs, which I don't think is very useful to go into now. So why is this important? Well, it tells you, it has some, I would say, different conceptual messages that this results, and which are somewhat surprising. The first one is the following. So this is a very strong positive result because previously, if you looked at shortest paths, it's well known that for shortest path, dynamic shortest path, you cannot get constant factor approximation. In the case where edges or this high accuracy 1 minus epsilon, which epsilon could be as say like epsilon, think of epsilon being 1 over 10 or 1 over 100, right? And it goes here into the running time too. But think of it being very small, okay? And so for shortest path, as I was saying, so there are lower bounds saying that this cannot be done. So you cannot have a dynamic algorithm that supports insertions or deletions of edges, or edge increases or edge decreases, and gets sublinear update times. Okay, this is not possible for short path, but it turns out if you change the way how you measure distances on graphs, and as I said, effective resistances are metrics, which are L2 squared, it turns out that you can do it, which is saying that you know, there's this kind of discrepancy between this notions of like how you measure distance of graphs and what can you do in terms of the dynamic complexity of this problem. And as you see, everything here that you see is a theoretical result, in a sense that, you know, we get this running time in a worst case. Probably our algorithms work better in practice, but worst case, we'll have this running time. So these are theoretical guarantees, okay? And there are also, so the second point is not really relevant because this is a bit more for experts who work on dynamic graph algorithms. But yeah, this is the surprising point, that for distances, you cannot get efficient dynamic algorithms, at least in terms of limitations. What happens in practice with heuristics is different. But for effective resistances, even though they look harder and they involve all these notions of like linear algebra and Laplacian systems, solving them efficiently, it turns out you can do better if you're content with very small approximation gradient. And obviously, this is not the right answer, I would say. These are the first results in the space, and I believe at some point somebody will not even get polylog running time. So that's the holy grail. So the holy grail is to essentially get a running time which is a polylogarithmic in the number of edges and nodes. Okay. Are there any questions about this set of results, or what these quantities mean, like update time, query time? I defined everything, hopefully, but if there are any questions, I'm happy to take those. If not, I can use some time to explain some technical stuff.
I think we'll have the time to ask questions in a few minutes. So.
Towards the end, okay.
Yes.
Sure, let's do that then. Okay, just a simple extension. We cannot just even solve this effective resistance query. We can even solve dynamic Laplacian systems. And you might ask, okay, how are you defining this dynamic Laplacian system? So here is one definition, which seems to be useful in other applications. So you have this underlying graph G and this underlying Laplacian, and these two are interchangeable. As you saw, there is a way of relating a Laplacian with the graph G and vice versa. You also have this demand vector B. In our case, it was 1 and -1 at S and T, but it could be anything as long as it sums up to 0. Okay, and let's say this demand vector B has small support. Small support, it means that the number of non-zero entries in the vector B is small, and by small, think polylog in the number of vertices and edges. Then you can handle the following operations. You can change edges in the graph, which corresponds to changing entries in the Laplacian. And you can handle all these operations in sublinear time. As you see, this is sublinear in the number of edges and nodes in the network. So irresponsible of what is the graph, irrespective of what is the graph density. So you'll get m to the 3/4 and m to the 5/6 running times. And the queries that you can ask is you can query specific entries in the solution vector X. And you can also ensure that the return solution, which is denoted by this X delta U. So this essentially, this is a good approximation with respect to the L norm, the induced L norm. So we can get extensions of these techniques for doing more things. I will not get into this, and I will also skip why this is interesting. And so whatever I told you in terms of results now, it can be achieved through just one very powerful technique, and this is the technique of this graph compression or vertex sparsification. This is very specific graph compression technique. And in the context of Laplacian systems, these are called spectral vertex sparsifiers, because Laplacian is tightly related to the spectrum of the graph, right? Okay, so let's start with some basics. I'm not gonna go much into like how to view this algebraically and everything, but I will give you very good intuition on why these optics are useful. So let's look at one specific example, which is the simplest, I would say, instance of vertex sparsification. It's simply a star vertex, as you see over here at this graph G. It has a center vertex, which is black. Remember, the black vertices are vertices that I don't care about. Red are the ones that I want to preserve. I want to keep intact in the sparsity. Okay? So now the question is, how do I get rid of the black vertices? Okay, and it turns out that if you get rid of this vertex from G, and then you have to put a clique on top of the neighbors of this graph H. So this, in physics, this is called data white transformations. In math, it's called, it has a different name. It's called the short complement. if you view this in terms of matrices, for those who have done matrix algebra. So that's the whole point. So what you do, you think of this, that you start with a big graph, and you have many black vertices and some red vertices. So what you do repeatedly, you pick one black vertex, you put a click on the neighborhood of the black vertex, and then you get rid of that black vertex. So then you keep repeating this until you have only red vertices, those vertices that you care about. This is pretty nice because it's a perfect vertex sparsifiers. And what is it preserving here? One thing that is preserving is it preserves all pair effective resistances among red vertices. Okay. Another thing it preserves is random walks between these vertices. Another thing it preserves is solution to Laplacian systems only restricted to these vertices. So it's a very powerful object. One problem with this is running time, right? So I do care about running times here. These are very slow because computing this small vertex sparsifier from a very big graph where I repeatedly remove black vertices cost me at least cubic in the number of nodes, right? And so unfortunately, I don't want to deal with this kind of running time. And so this is a perfect vertex sparsifier. Is exactly preserves all the properties that I mentioned. But the main problem is it has slow running time. And in addition, this graph A that I have over here is dense. Okay, so it's you think of it as a complete graph. Even if you have, so here's the thing, even you started with a star, right? This star is just a tree. It is a graph with no cycles. And then you're getting complete graph just after one illumination. So it's pretty expensive as an operation and gives you a very dense graph. So there are downsides to this. And the obvious question is like, how can we fix this? So here's the definition to fix this. So now you're given again, the same problem and given this big graph, it has black and red vertices, and I want to get rid of red vertices. So there's this notion of spectral vertex sparsifier. And this spectral vertex sparsifier preserves the spectrum of the graph, or the quadratic form of the graph, as you see this equation over here, among only vertices, only the red vertices, up to 1 plus minus epsilon factor. Okay, so that's the definition. So these graphs, these two graphs, the graph on top and the graph below, are spectrally close if and only if this definition holds. Okay, these are called spectral vertex sparsifiers. And now there is this great work by Rasmus King and Sushant Sachdeva in 2016, where they show that you can compute such structures in very efficient time. So this time is near linear in the number of nodes and edges in the graph, as you see here, OM. And also the size of the sparsifier compute is pretty sparse. So it's proportional to the number of vertices. So this graph that you see over here, it's sparse. Okay, so this is what I call the one-shot vertex sparsifier. This is the best as it can get. You know, you cannot get any better guarantees. And the question is this result helpful to us? So how can we leverage this result in terms of maintaining dynamic effective resistance sufficiently? So I've been thinking about this problem probably for the last 7-8 years, and I started some work with my advisor and a postdoc back in Vienna in 2018, and where we showed that, for example, for planar graphs, if you assume that this Laplacian that I give you comes from a planar graph, a graph which can be drawn on the plane without no intersection, so there is embedding of the graph in the plane, then you can use these objects as a black box to construct dynamic algorithms. And let me show how you do this. So here comes in the notion of clustering. So I have a graph G. I know it's planar, as you see. There are no intersections here. This is a planar graph. And it's drawn, you know, there's a planar embedding of this planar graph here in the picture for the sake of simplicity. So the main idea is you partition the graph into a few small clusters. And in addition, you also like that these clusters have very small boundary. And what do I mean by small boundary? I didn't put here numbers, but if say the size of the cluster is R, the size of the boundary I want to be roughly square root of R. Okay, that's what I mean by small boundary. So for planar graphs in particular, we know that they can be partitioned in a very nice way. This is called an R division partition of the graph. So what does it mean? So I'm taking the graph, I'm identifying these red vertices in the graph. And then this gives me edge-induced partition, because as you see, these two red vertices from different graphs are shared. So these boundary vertices are vertices that don't belong only to one cluster, but can belong to other clusters. And clusters can also have internal vertices. So this is the edge disjoint partition, but not vertex disjoint, because I can share vertices. And we know that one can compute such clustering of a graph efficiently in near linear time. Okay, fine. So we start with this structure. Now, for each of these graphs that you see over there, so you have this pieces of the big graph. I'm going to compute a spectral vertex sparsifier. I'm going to use that algorithm I told you as a black box. And now, remember, these boundary vertices are acting as terminals, these vertices that I care about. Okay, and so the goal is here to actually get rid of all black vertices from each of these clusters, or internal vertices. So vertices that edge is only incident to nodes in the same cluster. And I want to get rid of these black vertices, and I want to also preserve the spectrum of the graph only on the red vertices. Okay, I don't care about the internal ones. And I do this for each cluster. And that was pretty efficient, so I can spend time proportional to the size of the cluster. The clustering was cheap. Fine. Now, let's say I get an edge deletion from a user. Remember, I'm doing dynamic graph algorithms, right? So I'm going to have edge updates to the underlying graph. Let's say I get an edge deletion. If I delete this edge in the graph, then I go and find the cluster this edge was contained in, which is this graph here on top, as you see. And then what I'm going to do is then I'm going to just take the sparsifier that I had before, throw it out, and compute a new sparsifier from scratch. As simple as that. And now I know, like, you know, every cluster has a valid sparsifier, so the invariant is kept. As simple as that, nothing. Okay, so here I'm describing an only deletions only algorithm. So I'm restricting myself to only deleting edges, but can be extended to doing insertions. And now I have to tell you what happens if I ask a query between S and T. So what I do is the following. So I take the cluster that contains S, but I just take the cluster itself, not the sparsifier of the cluster. Okay, so this is very important. I do the same for T. I take the cluster that contains T, but not the whole sparsifier of the cluster. And then for each of the remaining clusters, I take their sparsifier, not the original one. Otherwise, I haven't done it, right? But because the boundary of this cluster is somewhat small compared to the original size. So now the size of my network is small. And now I will attach this graph back at the boundary nodes, because these are kind of connecting points. When I did this graph surgery, when I did this graph clustering, I made sure that, you know, I can patch the graph, this components of the graph back. Okay, so I'm going to patch everything together. So I get this underlying graph over here. And then on top of this graph, I can just I can solve a Laplacian system to find the effective resistance. But the caveat here is that this graph is much smaller than the original graph that I started with. Okay, and why? Because I found a way of actually removing internal vertices, and I knew that the boundary of all of these clusters was somewhat small compared to the size. So this underlying graph that I get from patching together now this sparsifiers combined with some original clusters, as you see over here, ensures that this is small. Okay, and if you do this naively, you can get an n to the 2/3 running time. So in planar graphs, the graphs are sparse. So number of nodes is proportional to the number of edges. And it doesn't make much sense to talk about m and n, so I can just talk about n, which is the number of nodes. And if you ask the effective resistance query in an original graph, it would cost you n, right? Number of non-zeros. But with this approach, after updates, I can answer queries in n to the 2/3. And n to the 2/3 is much smaller than n, right? Well, it's a polynomial improvement over basic query computed from scratch. Okay, and you can even improve this to square root of n. And I don't know how to go beyond this. This is still an open question. But you can do something else. You can do a hierarchy of these clusterings to actually bring down the running time to square root of n, the updated query time goal. I think this I couldn't cover much, but I tried to go into details, and I think it's a good time to stop for now. And I certainly Shimrim will share the slides after this. At least I've seen this with the other seminars, and you can have a look. And if you're interested, just let me know, drop me an email, and I'm happy to answer questions. And so I wanted to say one last thing. So I'm moving to Vienna soon as an assistant professor, tenure track. And I'm looking for students, PhD students. I have 2 positions, and of course the competition is going to be open, but I was very happy to hire even someone who is from my country and can do the work and is excited about this work. So just feel free to reach out in case you're interested about this. So thanks a lot. I will stop here. Thanks for listening.
Thank you very much for this very exciting talk, Gramoz. Faleminderit shumë. Do artrokitje nga distanca. Atëherë, në këto pjesë teknike të fundit që I përmende, faleminderit praktikisht për dorëzimin e slajdeve. Nëse ka ndonjë lajmërim për pozitat e lira që do t'i kesh, nëse mundesh më na dërgu, atëherë I vendosim në departament. Kurse tash po ja jap fjalën kolegëve, kushdo që ka ndonjë pyetje ose koment, Ju lutem lirisht. Artana, mos ke ndonjë pyetje ose po them Artani se po e shoh Artanin me të tjerë, kushdo? Nuk e di a ke ndonjë pyetje. Okej. Nuk po më duket që ka ndonjë pyetje. Për mua unë kisha një pyetje te metodat që ke prezantu, më thënë, rezultatin e fundit që e jep, se që nuk është detyrimisht kuptohet ai kufiri më I mirë. Edhe tash pyetja ime në përgjithësi është, kur I ke studiu këto grafe, a I ke studiu një herë disa grafe të veçanta, pastaj me pas mundësi me studiu edhe grafe të tjera në përgjithësi, a I ke këshyrë se përmende ato që kanë cikle, çush ka qenë ajo që çush ka qenë metoda për me pas të rezultat përgjithë?
Po, përgjithsisht qëndron pa kultura, për shembull, qysh matematicentat për në bojnë të rrit grafe dhe qysh algoritmicistat bojnë të rrit grafeve. Po, definitivisht kur, për shembull, sa I përket grafeve planare, për shembull, grid grafi, tash nuk po di kështu që është gridi, nuk e di që thonë në shqip. Në gridi është një ekzempull I mirë, që aty fillon
rrjeta apo?
Urna?
Rrjeta apo grid?
Rrjeta. Kështu për shembull grafi rrjet është I mirë, ka simetri shumë të mirë. Edhe simetria të ndihmon shumë me I simplifiku këto kalkulimet. Edhe për shembull për intuicion unë e përdori shumë. Për shembull, nëse du me bëj diçka për grafe planare. Për grafe generale janë quhen expanders, nuk e di a ka terminologji shqip. Janë grafe që janë shumë well connected, që për shembull distancat janë të vogla, I kanë të properties shumë të mira. Kështu janë disa ekstreme në të rrit grafeve që kur merr me kështu sanet prej perspektivës të algoritmeve janë shumë helpful. Unë I përdori kështu si bazë për intuit. Po për shembull, është shumë e vështirë me bëu një algoritëm që është I mirë në rrjeta edhe me publiku konferencë, për shembull, konferenca ose në journals të mira. Ndron edhe ka kultura të në, për shembull, nuk është, për shembull, unë është me pas rezultat, po nuk është shumë interesante. Se është çish më thon, bashkësi shumë e vogël e grave që njerëzve nuk ju intereson shumë. Thonë po kjo s'ndodhen në praktikë.
Po e qartë, edhe nëse tash ndoshta një koment shtesë se tash do ta lexoj edhe një pyetje ka Islami, se s'po mundet me thënë, po do thënë se aty po shihet që ka edhe aspekte topologjike, aspekte metrike etj, do thënë ka komponentet po e lidhshmërisë etj, se në algebrë nganjëherë është e rëndësishme edhe ajo sa a ka klik, a s'kan klik, domethënë ato që përmene. Po, le ta japim fjalën tash, ose pe fjalën, po në fakt po lexoj. Pyetjet që ka Islami. Islami thot, I was curious to know how much the results extend to non-simplicial graphs, i.e. the ones where one can have multiple edges between nodes, possibly with weights as well.
Po për shembull, po kjo ka generalizime, po mas ne vjen puna është pak problematike me modelim, me thonë. Për shembull, çka ka thonë Islami apo? Çka ka thonë Islami këtu? Për shembull, nëse ki grafe ku ka disa connections mes dy nodave. Atëherë unë është veç mi qitën paralel ato dhe mi bashku me një nodë. Edhe veç e merr shumën e këtyre weights. Kështu që ajo nuk është kurfar generalizimi. Këto teknikat që fola në këto bojnë edhe për grafe jo të thjeshta, për grafe që kanë weights. Okay?
Okay.
Për shembull, ka disa grafe tjera që quhen hypergraphs. Hypergrafe. Në hypergrafe për shembull nuk e lidh ti vetëm dy noda, po i lidh një subset of nodes. Për pra ato ka algoritma të tjerë, ka domethënë generalizime. Edhe për me studiu Laplace transform. Ka punë. Po këto normal në konfidu me sanet ma të thjeshta, dhe kështu që çdo ala të thjeshta s'po kuptohen mirë. Stili është ma mirë me kuptu të thjeshta në herë, mas ne me shkute ato.
Po, edhe potencialisht në fakt një pyetje tjetër që ndoshta veç studenti, po që teorikisht mund me qenë interesante është to pikat e kuqe që janë fillestare, do thënë ju e keni studiu problemin për çfarë do lloj konfiguracioni që janë ato me arrit me një rezultat, po qysh ndryshojnë rezultatin duke ndryshuar konfiguracionin fillestar, do thënë pikave të kuqe.
Po ka, për shembull në grafe planare, sidomos në grafe planare, nëse pikat e ki edhe nocionin e faqeve në grafe planare. Edhe për shembull, nëse krejt çdo pikat e kuqe janë në faqe, domethënë janë vetëm në faqe, nuk janë internalisht në graf, po vetëm në faqe, atëherë shumë ma lehtë është me studiu çto teknikat. Domethënë shumë ma lehtë është këto pikat që janë pikat e zeza me eliminu pi grafit, shumë ma lehtë.
Okay.
Domethënë varet që si ki, if they are well spread, domethënë si janë shpërndarë mirë e kanë një strukturë të shpërndarjes mirë në graf, atëherë mund është me pas shumë rezultate më të mira.
Fantastike.
Po, dhe aty studime.
Po. Fatkeqësisht më ardhur në Vjenë me bë një doktorat.
Jo. Mund është më ardhur në Vjenë edhe me bë histori.
Po. Faleminderit shumë jashtëzakonisht shumë Gramoz, me të vërtet i faleminderit në emër të gjithëve, në emër të kolegëve, edhe departamentit të tjerëve që janë jashtë, edhe shpresoj të shihemi së shpejti, ndërkohë shihemi në seminarin e radhës. Faleminderit edhe një herë, gjithat mirat, mirupafshim.
Gjithat mirat, faleminderit shumë.
Faleminderit.
Faleminderit edhe juve.